here. First off, it's my pleasure to welcome Professor Maha Haji to give today's control seminar. So I had the pleasure of serving as chair on the search committee last year that hired Maha. She's a new professor in mechanical engineering at U of M. She's not totally new to the world of academia and faculty. She was previously a faculty member, assistant professor over at Cornell. Before joining us, we're very fortunate to have been able to poach her from Cornell. Hopefully they're not too upset over there. We wind back the clock just a little bit. Maha did her undergrad degrees at UC Berkeley. I think, if I recall, I'm doing this from memory. After reviewing all of these applications last year, I know the bios pretty well. If I recall, was mechanical engineering and applied mathematics. And went on to do her PhD in the joint MIT Woods Hole Oceanographic Institute program. Went on to be a postdoc at MIT, and actually in her MIT days was doing a lot of research on mineral extraction, as I understand, from seawater and aqua environments. Could be kind of relevant these days, given the priorities of the current administration. But in any case, she runs a lab that focuses both on marine energy and marine robotic systems on one hand, and also multidisciplinary design optimization on another hand. So it's our pleasure to have her here today, presenting towards wave-to-wire optimization for wave energy converters. So let's welcome her.
Thank you for that really nice introduction, Chris, especially from memory. That's quite a feat, so thank you. So it's great to be here with you all and share some of the work that we've been doing in this space. But before I jump in, I really want to highlight that the work featured here is really done by my students. So a lot of the work I'll present was part of Kapil's thesis. He recently defended in the fall from Cornell. Some of the work is also contributed by Rebecca McCabe, who's a fifth year about to graduate from Cornell. And then our newest batch of students, Colin Tracy, is here at the University of Michigan, who's really taking the lead and building upon all of this work. And then I also want to thank funding sources. So the NSF gave Becca a fellowship, and then the DOE and Sandia have really been great partners in this work. So what I'll be presenting is mostly collaborations in many different ways and funded by Sandia for this work. So for my talk, I'm first going to convince you all of the need for multidisciplinary design optimization for wave energy and wave energy converters. And then I'll touch upon what we found to be the bottleneck in doing so, which is the hydrodynamics modeling of these wave energy systems. I'll present a differentiable hydrodynamic software that we developed to tackle that challenge in collaboration with Sandia called Marine Hydro, and then touch upon how we think this can be extended to not only solve the design problem, but the controls problem in a differentiable manner for wave energy converters. And then think what needs to happen if we are going to scale up from a single wave energy converter to a farm of wave energy converters and some of the challenges therein before wrapping up. So to start, why MDO for wave energy? Well, first, I'd like to give a brief primer on ocean wave energy. Ocean wave energy is considered a really important renewable energy source that we should tap into because ocean waves are very predictable, they're energy dense, and in many ways they can provide very consistent energy sources. They're oftentimes also complementary with wind and solar. So when wind and solar peak, usually waves are at a lull and vice versa. So for instance, they can peak in the winter when maybe winds are less in certain regions. In the United States, wave energy could meet 34% of all of our electricity needs. What I'm showing is a map of marine energy sources, and the light blue is wave energy, but the others are also things like tidal and river current. And they can be really interesting because wave energy can provide sustainable energy for distributed energy applications, sometimes called blue economy applications. So these are things like instead of sending energy back to the grid, you might use it on site at an offshore location for things like aquaculture farms, recharging underwater vehicles, maybe even doing desalination in disaster resilience response. And so they've really been looked at in that way. So where is ocean wave energy today? Well, the way that we extract ocean wave energy is using wave energy converters, or WECs, to extract the energy from the motion of the waves. And there's been many advancements in recent years. A company here in the United States called CalWave, they're based out in California. This is their pilot device that they tested in 2022 for 8 months, and it went flawlessly off the coast of San Diego. This is a developer out in Oregon called OPT, Ocean Power Technologies. This is their pilot device that they tested for a whole year in 2019. And I believe somewhere over here, I think there's like a person. So you can see the scale of some of these devices is quite massive. Recently opened out in Oregon is a facility called PacWave. This is an open ocean testing facility that was a collaboration with the Department of Energy in Oregon State and a lot of other entities. But the idea is it's going to be a wave energy test bed. Developers can come in, plug their devices into essentially the grid, and test how they perform out in the open ocean. It's going to be able to test up to 20 devices at 20 megawatts total, and it just opened this last year. So you're going to start seeing some of these developers out there. As you might imagine, the EU is a little bit ahead of us. So this is a company called OnDep that's going to actually deploy a commercial scale farm coming soon, 2 megawatt farm of wave energy converters. And then another company called Core Power in the EU, they had their full scale device tested for on the order of 4 or 5 years, and they have a 4 device array coming soon. So these systems are here, and they're really taking off, and folks are exploring all sorts of avenues. But there's a lot of challenges with extracting wave energy. And one of the biggest ones is that it has a high levelized cost of electricity. So what I'm showing here are 2 different types of wave energy converters. One is called the reference model 3 that moves in heave. So it extracts energy from the up and down motion that's induced from the waves. And the other is called RM5, reference model 5. It moves like a flap, so it surges when the waves hit it. And what I'm showing is data from the Department of Energy translated to 2024 dollars. And for both of these devices, their cost estimates come in at about $1 per kilowatt hour. That's extremely high when you compare it to current wind and solar prices. And I believe this also includes offshore wind, which is on the order of 4 cents per kilowatt hour. So if wave energy is ever going to be competitive for grid scale power, there needs to be a lot of cost reductions. What we feel in my group is that these systems are very complex, multidisciplinary design systems. They have interactions between their structures, their control system, their hydrodynamics, and their electronics. And so the traditional sequential design methods that have been used are quite limiting to unlocking their potential. If we look at traditional sequential design optimization when it comes to wave energy, usually folks start out with some kind of geometry. So for instance, might they think of a heaving point absorber or an oscillating surge WEC, come up with a general architecture. From there, they analyze the hydrodynamics. How do these devices respond to the ocean waves? Once we understand their response, we usually think about the structures. Okay, how do we design the structures and stiffen them in the appropriate way to handle these wave loads? And from there, once we can handle the wave loads, how do we extract energy out of them? What does that powertrain need to look like, that transmission system? And finally, control is usually an afterthought. All the way at the end, how do we tune this thing to maximize energy absorption, all with the goal of maximizing power? But what I hope you can see is that each step in this process limits the choices of future disciplines. So your choice of geometry locks you in to some assumptions you have to make about how your device behaves in the waves and its hydrodynamics. From there, you're locked in further into the structures and so on and so forth. So this is why traditional sequential design optimization for wave energy converters has a number of disadvantages. You often lead to suboptimal solutions because you ignore interactions that occur between these disciplines. And the results depend heavily on the optimization sequence. If I had started with another discipline, I will probably get out a different result. And adjustments in one discipline often require re-optimization of previous steps. So it can be very time consuming. This is very challenging for wave energy converters because they're inherently coupled systems. So I'm showing here a simple wave energy converter that can move and heave, so it can move up and down. And it's got some sort of power takeoff system that will convert its motion into something usable like electricity. If we assume linear potential flow, you can model a wave energy converter very much like a mass spring damper system, where you've got its body acceleration, velocity, and position. And on the right, you have the excitation force of the waves hitting the device that's causing this motion. So the components that go into this when you model it are the mass of the wave energy converter and something called the added mass. This is due to the inertia of the water moving with the wave energy converter. You also have damping in the system. Some of it is due to the energy radiated as the wave energy converter bobs up and down. It's going to radiate waves. And some of it's due to the powertrain, your PTO damping, usually set by your controller. And there's some amount of stiffness in the system, some amount of hydrostatic stiffness that's due to the general buoyancy of your system that restores it, and as well as your controller. If I color code these, I can color code some of them as red that are related to the geometry and the structures of the device, and some of them as blue that are related to the powertrain and controls of the device. So I already see that these two disciplines are interacting just with a simplified governing equation of the system. Another way to think about it is if I'm looking at the design space of all possible choices in my geometry and all possible choices of my control system, if I optimize the geometry, maybe I might operate in some region here. And then operating on that line, I have to pick a controller to maximize my power. So maybe that looks something like this. And this solution that I achieve at this intersection is actually likely suboptimal. If I look at the full design space, here I'm plotting contours of minimizing an objective and maximizing an objective, you can see I've entirely missed this true optimum because I couldn't explore the full design space. So the sequential design that has often been done for wave energy converters really limits its potential due to this ability of neglecting coupling. And there's coupling in many different disciplines within wave energy converters. Generally, the main disciplines in a wave energy converter are its geometry, its hydrodynamics, its PTO or powertrain, its control, and its structures. Often there's coupling between the hydrodynamics and the PTO. So the hydrodynamic response influences the PTO's ability to extract energy efficiently. And at the same time, the PTO will induce forces on the wave energy converter, impacting its wave radiation. You'll have coupling between the control system and the PTO and the hydrodynamics. So your control strategies adjust your PTO settings based on wave conditions, and the control inherently affects the WEC motion and consequently its hydrodynamic and PTO interactions. There's interactions between the hydrodynamics and the structures. So the hydrodynamic forces will determine the structural stresses and fatigue life of your system. And the structural design affects your hydrodynamic performance, including your energy capture and stability. And finally, the PTO and the structures are very coupled because the PTO generates forces on your structure that you have to be able to handle. But at the same time, the structural compliance of your system may influence the PTO efficiency and its ability to extract energy. We believe in my group that multidisciplinary design optimization can help address these challenges, because the idea with MDO is that it captures the interactions between disciplines simultaneously, leading to eventually globally optimal solutions. So we look at all the disciplines at once with some overarching objective, in this case, maximizing power. And the idea is by considering them simultaneously, we can get to that globally optimal solution. And this simultaneous optimization reduces the need, therefore, of iterative adjustments. And if we think more generally about the design process, generally when you go through the design process, you gain more knowledge about your design in this solid blue line, but your design freedom greatly decreases because now you're locked into a specific design. What MDO tries to do is it tries to give you more knowledge about the design earlier because you consider your disciplines earlier, and therefore you can explore more conceptual designs and have more design freedom longer into the process. There's been work already looking at optimization for wave energy converters. I'm going to highlight some studies. Most of them have primarily focused on specific subsystems, but more recently, people are considering more and more subsystems together. And in general, MDO is used widely in aerospace and automotive industries and is taking off in offshore wind design. And so these studies, they don't explicitly consider MDO, but I see what they do as being MDO in practice. So one example was a study that tried to optimize the layout of an array of wave energy converters to maximize power and minimize transmission cable length. So they had disciplines of the location of the devices, they had the transmission cable, and they had power. Another couple ones looked at optimizing device geometry to maximize power and minimize joint fatigue. So structures and geometry were involved, or optimizing geometry and location to balance power production and structural reliability. So again, structures, geometry come into play. And more recently, there's been a lot of work in a space called control co-design, a subset of MDO, where folks have been trying to co-optimize the geometry and controls to measure, maximize power, co-optimize the PTO controls and to maximize electric power, to optimize a flap geometry, its PTO and controls, all to maximize power. So this space of control co-design is really picking up in wave energy. But all of these studies use non-differentiable, computationally intensive numerical models for their hydrodynamics modeling. And therefore, they end up doing parameter sweeps for optimization, so brute force optimization, because they can't do gradient-based methods, or they use heuristic optimization techniques, which really limits rapid design iteration. And I really like this figure, and I'll come back to it. This is from a book by Kim Martins. And it looks at the different ways of different types of optimization algorithms. So on the x-axis, I have the number of design variables, and on the y-axis, I have the number of function evaluations. And if you're able to use a gradient-based analytic method, those scale the best as you increase design variables. As you go to finite difference methods that are still gradient-based, that's less so. And finally, those gradient-free heuristic methods scale the worst with design variables. So if we're going to look at wave energy converter design in a complex sense, we really need to be in the space where we can be leveraging analytic gradient-based methods for optimization. Otherwise, we're going to be limited in the complexity of our problems. What we found specifically is that hydrodynamics has been the bottleneck for the most part in a lot of these models. So let's talk a little bit about hydrodynamics modeling. So here's that governing equation I mentioned again. And what I've highlighted are what we call the hydrodynamic coefficients. These are the added mass, the damping, and the excitation force on the wave energy converter. There's a couple of different ways that you could compute these. They can either be found numerically or with semi-analytic methods. You can also use CFD, but that's a lot more computationally intensive, so I won't mention that here. One of the most common numerical methods is the boundary element method, and it solves the problem in the frequency domain. It's faster than CFD and works for any geometry, but it's still computationally challenging and not analytically differentiable. And that's why folks, when they've used it, they've paired it with intensive gradient-free and heuristic methods for optimization. On the other hand, there are semi-analytic methods. One example is the matched eigenfunction method that we've been expanding in my group. It matches boundary conditions at the interface of fluid domains around the body. And so it's very computationally efficient and analytically differentiable, but it only works for cylindrical geometries right now, and it can't handle wave energy converter arrays. So it requires considerable simplification of geometries and problems if you're going to use it. But just to highlight how fast the difference is, if I were to do the same hydrodynamic model using these two methods, my semi-analytic method versus my numerical solver, I can get 30 times speed up with my semi-analytic method. So if I can simplify my geometry, that's the way to go. What I'm going to focus on this talk is on the boundary element methods that we've been working on that allow us to work with more generalizable geometries. So how is hydrodynamic modeling done in boundary element methods? And I'll give you a very quick primer. So instead of solving equations everywhere in the fluid volume, like CFD methods do, boundary element methods only consider them on the boundary. They say it's really just the boundary that has interactions with the waves. So let's see if we can focus on that. And if a flow is inviscid, incompressible, and irrotational, you can simplify things quite a bit because the velocity field comes from a velocity potential. So phi can be written with the Laplace equation it satisfies. And with the Green's second identity, we come up with this equation in boundary element methods, where P is some point on the boundary that I'm interested in. C of P depends on the boundary. It's usually 1/2 for smooth geometries. Phi of P is the velocity potential at that point P on the boundary. G is the Green's function that comes up a lot of times when we see the Laplace equation. And d phi dn is the normal velocity on the boundary, where gamma is our boundary. What boundary element methods often do is they'll then discretize the boundary into panels and try to approximate phi and d phi dn at each panel. And what they do is they basically are able to turn this integral equation into a linear system subject to boundary conditions that we have on the body surface, on the free surface, and at infinity, meaning that the waves radiate away. So boundary element methods can then allow us to recover those physical quantities, added mass, damping, et cetera, because they're all related to phi. And so they're really powerful because they basically transform the 3D problem or through the whole domain into a 2D problem along the boundary. And in particular, they also, to solve this integral equation, they come up with matrices, complex valued matrices that are defined throughout the boundary. So as I mentioned, we found that hydrodynamic modeling is the bottleneck for MDO in wave energy converters. And that's because even though BEM is fast, it's still computationally costly for large scale problems. I mentioned we have to discretize the boundary. So we have some amount of meshing that goes into there. So we have to solve this phi at all of those boundaries, at all of those panels. And when you think about design optimization, you have to run your simulation hundreds or thousands of times. So if I have a simulation model here, some design vectors and some objectives and constraints, my optimization algorithm will wrap around that. So the faster my simulation is, the better chance that I'm going to be successful in optimization. Gradient-based optimization methods are often the fastest, as we saw, because they scale better with design variables. But current boundary element method solvers are not analytically differentiable. So it means you can't take analytic gradients and then leverage gradient-based optimization. And folks have either used gradient-free or heuristic optimization, which is computationally intensive. You could potentially do differentiable programming with existing boundary element solvers by leveraging finite differences. But finite differences can suffer from inefficiencies and truncation errors. So if we were to approximate, let's say, d phi dx, where x is a design variable, using a finite difference, we have to compute phi ahead and behind of some step size h, or some small perturbation h, in each input variable. And so each input perturbation requires 2 boundary elements solved, which is already computationally intensive for large problems. And I have to repeat this for every single input variable x, so every design variable that I care about. So it really scales very poorly computationally. And therefore, these finite differences are expensive because every time you solve a boundary element instance, you have to evaluate the Green's function and that integral that I showed before, which has complex value dense matrices. And then I have to solve it for each perturbation, every single optimization that I go for. And again, even if I am using finite differences, they don't scale nearly as well as analytical methods. So that was really the goal in the work that we took on with Sandia, is can we create an analytically differentiable boundary element method to solve this hydrodynamics bottleneck? So with that, I'll touch upon what we've done with something called marine hydro. So marine hydro is a completely differentiable boundary element solver. This is just a schematic of what it of some of what it does. So you can mesh the body surface. You have a wave environment. It computes those matrices that I mentioned, those complex valued matrices related to the Green's function. It can either use the direct or indirect method for boundary element methods. And it implements both an exact and a surrogate Green's function expression. So there are ways to approximate the Green's function, and you can speed things up a little bit. And we've shown that that still works well for optimization, even as an approximation. It's 100% in Julia, and that's what really allows us to do this kind of differentiable optimization, because we leverage a lot of the differentiable capabilities in Julia. And we implement the adjoint with automatic differentiation for this. So if you're interested in the details, we have a couple papers here, and all the code is open source. We have tutorials. We'd love, if you want to use it, happy to talk. And Colin is extending this work, so it will be, future versions will come out. But to give you a little bit of a look at how it works under the hood, so let's say you've got some design variables that you're interested in theta. You can input those along with your geometry into the solver. It will compute those complex valued matrices, compute a linear solve, and get your potential. And through post-processing, you can get some sort of objective that you're interested in. So that doesn't work any different than current boundary element methods. But what really allows us to do more is that every time you assemble these boundary element matrices, we also leverage automatic differentiation so that we can instantly build up a map of these functions and get their sensitivities. We also leverage the adjoint, which I'll talk about in detail in a little bit, to get more of those sensitivities. And that allows you to get the gradients that you care about with respect to those design variables for any objective function. So how do we do that? So let's say you have a scalar objective that you care about, like maximizing power in the case of wave energy converters. And it's a function of your potential phi as well as some design variables that you have, theta. It's subject to a constraint. So this is essentially recasting that Green's second identity integral I showed, where D and S are complex valued matrices defined at n number of panels. Phi is the vector of potentials on each panel, theta are my design variables, and B is just my normal velocity, and J is my objective. If I were to compute the total derivative of J with respect to theta, I would need to compute this, partial of J partial theta, plus partial J partial phi partial theta. And it's this partial phi partial theta that's really challenging. This is because theta are my design variables and phi are the potentials at my panels. So it's only defined implicitly via the constraint. And I don't want to compute this if I don't have to, because I have to compute it for every panel, for every design variable. I really don't want to do that. So we can differentiate the constraint applying the product rule. And if I were to rearrange to solve for d phi d theta, I would have to solve this for every single theta on every single panel if I wanted d phi d theta. And that's computationally expensive. We want to avoid that if we can. So instead, we define something called the adjoint variable. And this is done a lot in aerospace optimization. So lambda is defined by this equation where we have that matrix D, lambda transpose times that matrix D equals dj d phi. I can rearrange some things and combine it with the previous equation. And eventually, I can write the total derivative of J with respect to that adjoint variable lambda. And I don't have to compute d phi d theta at all. And that's what I wanted to get away from doing. So by doing the adjoint, this is just one additional linear solve. We can get the derivative of J with respect to theta. So this is very computationally efficient. We avoid computing d phi d theta. Therefore, we can have efficient gradient evaluation for large systems. And in fact, we tried it out. So here is doing our automatic differentiation and adjoint as we increase the number of design variables versus if you were to finite difference with an existing BEM solver. So we see it's always two linear solves. It doesn't increase time with design variables. So instead of having a problem where it depends on the number of design variables, how fast it takes to solve, it's always just 2. And in fact, you can reduce the computational cost even more, where n is the matrix size and m is the number of design variables with with this trick. And then we can also use factor-based solvers like LU decompositions to reuse some of our computation and reduce the complexity even more. So the complexity still scales with n, where n is the number of panels. But it's really easy to compute the adjoint matrix. It turns out it's the transpose of our forward matrix D. So what information can this tell us that we weren't able to get before? Well, I'll just share one example. So one question that often comes about in wave energy design is how close can you place your wave energy converters or before you worry about their interactions? Or how far apart do you have to space them such that you don't have interactions between them, that their wave fields don't interact? So let's say we've got 2 spherical wave energy converters here. Based on some numerical studies in the past, the cutoff distance is typically taken to be about 5 times the characteristic dimension. So in this case, about 5 times the radius. And that was just done through numerical studies. Well, now with marine hydro, we can actually compute the sensitivities analytically. And here what I'm plotting is how sphere 1's added mass and damping change with respect to distance to sphere 2. So sphere 1 is in the green line, and its added mass, and its damping is in the orange line. So ideally, we don't want that added mass or damping to change at all, no matter what the distance is and the radius is of sphere 2. And we see that that drops off right about that cutoff that's been theorized by Singh and Babarit in 2013. So we line up well with existing literature, but we can do so much more now that we have this tool with the space of design optimization. So how might this fit into not only the physical design optimization, but also optimizing the controller for this system? So in wave energy converters, we often call that problem the wave to wire problem. So you might have a design of a wave energy converter. You can compute its hydrodynamics with, let's say, a boundary element model, what we call the wave model. And then for that specific wave energy converter, you can optimize its control trajectory to maximize power. And you might subject to some constraints on your PTO, like force saturation. Another way to think about it is I have incoming waves, and I have some design variables that influence my design of my wave energy controller, my absorber. I've got some design variables related to that power transmission, some design variables related to that electrical generator, all with the goal of converting power, let's say, to go to the grid. So this half of the problem we call the wave problem, which hydrodynamics helps us solve. And this half of the problem we call the wire problem, which is a controls problem. This ends up being a very high dimensional problem. And therefore, we require gradient-based methods if we're going to have any chance of being successful at optimization for the entire system. And because of that, we really require end-to-end differentiability through the wave model as well as the wire model. So we've surveyed the literature, and we feel that doing this with gradient-based methods would really enable the use of high-fidelity solvers. And the nested optimization model is probably the most intuitive for incorporating the wire model with the wave model. And this is some work by Herbert and Allison. So what do I mean by a nested formulation? So in this case, I have an outer objective, which is basically to optimize my WEC design to maximize some function of power. This could be power per unit volume. This could be cost with power incorporated in there, something that I care about, subject to my constraints and solving the boundary element equations. And then within that, I have a wire model where I want to optimize control to maximize power. And I have to be subject to constraints on the WEC dynamics, as well as subject to constraints on perhaps the force limits of the PTO and perhaps there's other limits that I care about. Another way to look at this is through what's called a design structure matrix. And so the way to read this is you have your optimizers and your disciplines on the diagonal, and you have the feed of the variables to the right. So my design optimizer has design variables X that govern the design or the geometry of my structure. Out of that, I get some design variables that my controller also sees and solves the dynamics and control problem. And out of that, I get power. And then that goes into a function of power that my outer optimizer sees, whether that's power per unit volume or levelized cost of energy that uses power. So what I want to highlight is that for every design that my optimizer looks at, I have to solve this controls problem for maximizing power extraction. So there's a different solution for every single design to maximize power extraction. So at each iteration, I have to solve another optimization problem for the controls aspect. So for the wave model, I can use marine hydro. It can give me my hydrodynamic forces and added mass damping. I can have differentiability with it because I can do forward mode differentiation, and I can achieve a backward mode differentiation with my adjoint methods. My outputs include the sensitivities of my hydrodynamics to my different design variables. So whereas previously a traditional boundary element solver would just give me my hydrodynamic performance, I can now get my hydrodynamic performance and my sensitivity of performance. So I can use that for gradient-based methods. For the wire model, we're looking at WECOP tool. So it computes the optimal, it's a toolbox that can compute the optimal PTO force trajectory for wave energy converters by maximizing the total energy absorbed by a wave energy converter over a time horizon. And it does this really efficiently using something called the pseudo-spectral method for trajectory optimization. So if a traditional solver would step through time to reach an optimized trajectory for your controller, WECOP tool and the pseudo-spectral method does it in basically all at once using basis functions in the pseudo-spectral method. And this has been developed by Sendia National Labs for wave energy converters. And what it basically does is it turns the optimal control problem into a nonlinear programming problem that I showed earlier, where now you are minimizing some function subject to WEC dynamics and PTO force limits. And that function might be your average power delivered to the grid while considering the governing equations of WECs and any path constraints. This could be maximum PTO force, but it can also be displacement constraints and so forth. So what I want to show here is that if we're going to differentiate the wire model, it's basically differentiating a whole optimization problem in and of itself, and that's a challenge. So we're still working on this, but some of the avenues that we've been working on is to differentiate through that optimal control problem. We're using the Karush-Kuhn-Tucker conditions to differentiate that inner optimization. We can also extract post-optimality sensitivities using the Lagrange multipliers. In fact, we rewrote WECOP tool to use IPOPT instead of, I believe it was using SLSQP as an optimizer, because IPOPT gives you the Lagrange multipliers. And this can avoid brute force finite differencing of the optimal control problem, because we don't want to do finite differences as they introduce numerical errors. Then to couple the wave and wire sensitivities, we can use unified derivative equations. This is basically an extended version of the chain rule. And there's a framework built into a Python package called OpenMDAO that does this. You can mix adjoint, forward mode, analytical, and finite differences for efficiency. And the total derivatives can then be assembled systematically. So it works really well. We think that there'll be a lot of simplifications and efficiency gains here by leveraging something from Sobieski. He was a leader in MDO, where you could evaluate the derivatives of the Lagrangian at the optimum using his estimation method in a way that allows you to avoid second order derivatives in computing your sensitivity. So we've been implementing that. You can have soft penalties for inequality constraints to keep the optimization differentiable. And then the chain rule assembly really allows for scalability when we're combining derivatives from the wave and wire model. And so some thoughts we've written up in our ASME presentation. This is still a work in progress. So this is what Colin has been taking up the mantle of. And hopefully in a future talk, I can share some interesting results. But if we could do this, how might we scale it up for some wave energy converter farms? Well, one of the things I want to show you is how boundary element methods and that optimal controller scale with a number of wave energy converters. So here I'm only going up to 9, and you can see the computation time for these methods really is increasing drastically. And therefore, current research in wave energy farms either limits the number of wave energy converters modeled or neglects any of the interactions between them that occur in the farm. There's a method called multiple scattering for hydrodynamic modeling of wave energy converters at arrays. It can use the boundary element method properties, the hydrodynamic properties of a single device, and then interaction theory to compute the forces for the whole farm in a more computationally efficient manner than boundary element methods. And so we're looking at trying to develop a differentiable version of multiple scattering so that we could do WEC farm modeling and optimization efficiently. And at the same time, WEC-op tool does not scale well with more than a couple of WECs. So we're trying to look at modal decomposition as a way to reduce computation time for the inner wire problem. And if we could do that, we think that we'll be able to really speed up computation time for both the wave and the wire model part of this. And what that might all look like together is you might put in your isolated wave energy geometry. Marine Hydro would be able to compute that. We would solve the isolated problem and the interaction problem for the farm based on your farm input parameters, and then solve the optimal control problem and eventually be able to do full farm power and sensitivities. So to wrap up, our goal with all of this work is to really drive advances in wave energy converter R&D. And there's a great picture from John Ringwood's group at Maynooth from a paper in 2021. And these were the R&D topics that they considered for wave energy converters. And in general, the current focus has really been on wave resource assessment, WEC concepts, hydrodynamic modeling, and PTO innovation and control design. So these are all concepts in the inner ring. And all these outer ring topics are still underexplored. And so we feel these sorts of things like combinations, optimization, survivability, WEC farms, we think all of this is really going to need to leverage things like MDO or CCD control co-design to help us analyze those topics and optimize designs. So with that, I'm happy to take any questions. As I mentioned, all our code is open source. All our papers are here, and happy to share any tutorials if you want to try this out for yourself. Thank you. Yeah.
I've used WEC-op tools as well. It has simple functionalities. I think, if I'm understanding it correctly, what you're doing is basically like
Yeah, so it is, I would say it can give you the theoretical maximum, but it might not actually be what can be implemented in the field.
So just curious how long is the duration?
Mm-hmm. Yeah, we're still exploring that. So I don't remember.
Still not experiencing you like it.
Yeah. Yeah, no, that's a good point. Thank you.
I thought I had seen that optimization treating Yeah, I was wondering myself, having not used web tools.
Yeah, great question. So we can do irregular waves, but they're specific to some, significant wave height and peak period. So you'll have to basically do a sweep if you actually want an idea of what's happening at a specific deployment location. And we have some other work, not with so detailed control optimization, where we look at optimization under uncertainty in those wave parameters, in the directions and the significant wave height. And so when you capture uncertainty, your estimates for power really decrease drastically. And so that's something that we're also seeing.
Any questions?
Yeah, great question. So with wind, they've been able to leverage a lot of what's happened in aerospace. So aerospace has really pushed the field, and Kim Martins in particular, in the space of MDO and how to do that computationally efficiently, how to come up with reduced order models and so on and so forth. So at least for the turbine portion of wind, my understanding is they can leverage a lot of what's already done in the field. But you do have the same challenges come up when it comes to the wave interactions problem if you're looking at offshore wind, and how do you model that? And so far, because there's been no way to differentiate the boundary element method or the hydrodynamic solver, they've done some assumptions, they've made some scaling arguments that's kind of simplified the problem to allow them to do some MDO. So you can, and people have done it, but we believe they're inaccurate by doing so. And we actually think that even in the case of the what folks have done in wind, they've done it just so they could actually solve a problem. But I think there are a lot of interactions in the wave structure problem that aren't captured when you do those things that can be really important. Sometimes it's more important in the case of wave energy, because in the case of wind energy, you just need to sort of ride out the waves, and understand how their response influences your response. Whereas with the waves, you actually need to tune your controller so that you can harvest the incoming waves and sort of, in a way resonate with what's coming in so you can extract the most power.
Here's a nagging one in my mind. So I mean, this work on the differentiable solver approach, fluid dynamics, own right, it seems extensible outside of the wave energy world, right? Sources. So if we focus on the wave energy world, presented this bar chart beginning of the presentation where point absorbers and flaps, where you're trying to get from basically $1 per kilowatt hour to 4 cents. The question in my mind is MDO going to be enough to get you there, or do you need fundamentally new creative design and vision? Analogy I would make is with
Yeah, that's a great question. So we have a paper coming out, where we've applied MDO to an existing architecture, that RM3, and we've been able to get the cost from $1 per kilowatt hour to on the order of 30 cents per kilowatt hour. So it can certainly help you, but it's not going to be the only thing, we think. And so I think thinking outside the box for radically different designs is going to be necessary if you want to hit these utility scale costs. But there's been some other work that suggests that even if you're 2 to 3 times the cost of wind and solar, when you think about the whole energy mix and the need for reliability in that mix, it still might be cost effective on the whole to include wave energy than not. So maybe you don't have to get to 4 cents, but you certainly have to get closer than I think 30 cents.
There may be some markets that stand to benefit from the 30-cent island community.
Yeah.
Small markets, but certainly they would provide a small fraction of the chart that you put up that showed the technical research.
Yeah, absolutely.
Other questions? You got 8 minutes.
Mhm. Yeah.
Have you looked in that direction? Maybe.
Yeah. So we did explore that first because we're like, let's start with a simpler problem. And then, and we were able to solve it and it's in, I believe it's in our paper. But then we looked at the constraints and we're like, okay, maybe we should be looking at these because they can have a real big impact on the ultimate power output. And so that's why we lean towards wet gap tool because they already have a really great way of implementing those constraints. And that's before we understood some of the computational challenges with wet gap tool. So we're still, exploring options for solving this wave to wire problem, I would say for sure.
Can you do a linear approximation for this, please?
Thank you, everybody.